Hello, friends. This is first live session on risk-based engineering. Probably, I would like to see uh, your experience, some questions. If you have, I think this is fourth week is over. I guess you can update me on this. And if you have any questions, please ask now itself. Thank you. When you ask question, please give which lecture, title of the lecture, and specifically if you can indicate which slide, or otherwise you can ask question, no issues. We'll try to figure out. Hello, friends. If you are there in this session, please put in the chat box your name and where from you are. I am Professor Prabhakar V. Varde. I have come to IIT Bombay NPTEL studio to have a nice interaction with you because 4 weeks are over, it seems. So you definitely must be having some questions. So please put in the chat box whatever questions you have. And my team here in the NPTEL center, they were all set in the electronics and communication portal. If you are there, you please write your name in the chat box. And if you have question, even if you don't have a question, you show your presence by typing your name in the chat box so that I'll know that you are. I have a few learners around to interact. Hello, friends. If you are there, please indicate in the chat box that your name and you are attending the session so that I'll know that I have few learners in this session. Okay, till you ask a question, I'll keep talking about this course. Basically, this is a unique course on risk-based engineering for reason number one, that this is a new subject which has been created, using the traditional approach and the relatively advanced new approach, that is probabilistic risk assessment. These two, when they integrate, either it becomes a risk-informed or risk-based approach. Why I'm calling it as a risk-based approach? Because even we are trying to integrate the deterministic component with the probabilistic component, and they are basically complementing each other. If you have a risk-informed approach, that means the probabilistic component support the deterministic approach, and that's why we say that deterministic approach plays the primary role, whether it is design, operation, maintenance, and all that. Now, why this approach has come? The reason is the complex engineering system started evolving since 1950, especially the safety critical systems like nuclear plants and all that. And now we have adequate experience, and that experience is getting translated into the data. And of course, we are not having, even now, there is a huge requirement for data. But then you see, earlier we were going by experience and some calculations, deterministic calculations. But now we have performance factor also, which is coming in through the data. So these two gives us the more confidence, and when you integrate these two components, that is deterministic and probabilistic, it becomes a more holistic. So So the integrated approach, it provides an opportunity to be having a better view of the situation, whether it is design, decision making, or it is operations, it is design of new components. So one simple example, factor of safety plays the key role in design traditional design approach. But here we have the concept of uncertainty, and this tells us based on the data um, what is the strength of our calculation and what are the margins that are available. So we have a quantified metrics for taking decision, and decisions are based on risk metrics. So we are again sort of having a improved framework in terms of a quantitative approach. You know, so this is the gist of it. And then when it goes into the field, this approach is more amenable to real-time solutions like maintenance interval optimization, or generally maintenance optimization, because you have data with you which component was failing in which failure mode. And then the maintenance programming becomes more dynamic in the sense that suppose if there are more failure of certain type, and then the maintenance or inspection should focus on those areas which are better identified and prioritized in a risk-based approach. And second thing is, let's say simple example, how frequently a component needs and maintenance. So here we have failure data, and we have component characteristic. So we can work out a very rational based approach for inspection or maintenance. Similarly, if I develop a operator support system for emergency condition, normal operation and emergency condition, and then using the risk assessment framework, we have a better insight into how the situation will evolve, which are the critical components which have come based on the ranking and prioritization, and and then you can say in the dynamic sense how the situation is evolving through faulty and inventory approach. And of course, nowadays it's time to go for more dynamic. So the traditional approach we have on risk assessment, the faulty inventory are static in nature. But now a dynamic component is coming not only to faulty inventory, but the whole gamut of probabilistic risk assessment. So that in a sense, down the line, few years, and we will have a dynamic risk assessment. Dynamic risk assessment is the model for us. So we will be able to better simulate all the postulated condition in the sense of which direction the scenario is evolving and what are the needs of that hour, especially for emergency conditions. So overall, this is a new tool, and of course, every tool you have to modify, you have to update, and that requirement is always there, and it is a recursive procedure. So, but then, for example, in this approach, that is risk-based engineering approach, the human factor, there was a special attention on human factor. That is one model, CQB model. The concept of consciousness and cognition form integral part of human factor analysis, point number one. And then you can see the physics of failure is a new approach. And this physics of failure approach, along with the data analytics to support the prognostics and health management. That means now we are focusing on remaining useful life. So there are two components of degradation and its performance. One is that frequency of failure. Uh, it is very useful in prioritization, identification, and all that. But when the situation is evolving in the plant and a decision has to be made, what is the next step we should do? Whether we should carry out immediately the maintenance, or we should push it to the next. So if you have a trending of degradation, then you are better equipped with a matrix which can form part of the decision making in terms of plant maneuvering, shutdown, operation, lowering, increasing the power. And I think that is a beautiful dimension that we have. Of course, in prognostics also, primarily it has been developed for electronics, but mechanical components also there are in electrical, especially the digital, especially if we call power electronics. Digital and power electronics, we have some challenges in terms of like digital electronics. There is a software component sitting, and in software component, especially for complex engineering system, there is no uh, generally agreeable solution. Why? Because software, if it is, suppose there are three redundant channels, and of electronics, and in the all the three channels the same software is sitting. Now if there is some problem in the software, it affects all the channels, so that means you have a complex component of common cause failure. Okay, so that's why safety critical industries, they basically uh, they basically have this one channel which is independent, diverse, and it should be based on the traditional electronics. That is, let's say, solid state logic, which came in 60s and 70s. So, and the other can be digital. So, still the reliance on digital is less. Point number one. Point number two, when we talk about the power electronics, the stresses in power electronics are very high. Let's take the case of a capacitor. Now, the capacitor in power electronics, they are in hundreds of microfarads, and there are problems of their failure, their performance, and then the power electronics, they operate at normally relatively at a higher we can say stress levels in terms of temperature, or humidity and all, because they are very big, unlike microelectronics channels which are there located in the panel, and then we ensure the power electronics equipment, they can be in the field, and so their failures are expected to be higher. That's why the factor of safety is, if I require an inverter of, let's say, 20 kilowatt, then I'll go for a 40 kilowatt. So that way, derating. This is called derating of operations, or design, and that's how we are operating. So extensive work is going on. The major components are solder joints and the capacitors, and then IGBT. These are the components that are there where we need special attention. So these are the things that we have to see. And you must keep one thing in mind. There are certain issues with the complex system. Though in design, huge provisions are made that common cause failure is one issue. Common cause failure should not occur because it kills all the redundancies. So that's why the traditional principle of separation, isolation, and location, and then having a redundant design to some extent, if possible, they are there in design, no problem. If because you have to say common cause failure, one could be external event, other could be internal event. Let's say flooding is some outside the plant, some flooding has happened, and then water enter into the plant areas. So the same flooding water should not kill your redundancy. So that's why first of all, the location of the systems are redundant systems, and their junction boxes, and then complete inventory, whatever possible, so that we don't have similarly fire. So we have a separation between two redundant system, two or three redundant system. A brick wall is created, or whatever separation you want to have, which has capability not to affect the performance of the component. So one is common cause failure. Other one, as I told you, software reliability. Software reliability has come a long way. It is being used in different fields. But if we talk about uh, complex systems, complex engine system, we have to be very careful. because same set of software or configuration, and in such system there is not a very option to have the software from different sources, because then integrating them, and people were talking about it, but it doesn't appear to be a very attractive solution. Okay, so software is one of the things. Then you may be knowing the human factor is one of the major contributing factor to the. In fact, human factor is the key factor that has ensured safe operation of many complex engineering system, and we are benefiting from that. When we have continuous power supply in our home, and then our industries, they are operating, the production comes from there only. But uh, the operations are relatively more human action interactive, and let us accept it that the human errors should be as less as possible. But if we see at the same time, in spite of all these benefits, if we see that industries, what they are doing, uh, the analysis shows that the contribution from human error ranges from 50% to 70% or little more. And that is the insight from most of the major accidents. So, you know that accident don't happen just because of one fault. You require chain of faults. And um, a common cause combines them, but okay. So suppose the one system was there, it did not perform. Second redundant system was there. You might be knowing difference between redundancy and diversity. Redundancy means similar equipment um, are operating in parallel, or provided as per the design in parallel, so that they can take one fail, second comes. But then in diversity, they should be having two protection channels or two safety system. They should have a different principle of operation. Like one system, if it operates because of withdrawing the power supply, okay, then the other system should be operating on gravity driven water or somewhere. Like so, both are independent. Like suppose there is a seismic event. Now, if seismic event can fail because of vibrations and all, one system, it should not be failing the other system, because other system operates on a different principle. Let us understand it through some example. We have a cooling system for our operation. Now, cooling can be provided by motors, and cooling can be provided by water driven turbines also. You see, both are having a prime mover. One is electric prime mover, other one is a hydraulic prime mover. Now, if electricity goes, then we have water turbine, which is operating. So both are operating. For water turbine, the water has to come gush from a tank which is located at certain elevation, at higher elevation rather, and then it operates the turbine, and turbine operates the pump. Motor is operated by electrical power supply. So if water is not there, electrical power supply is available, and our purpose is met. And um, uh, if so, any one of the source should be there. This is called diversity. So this is how we have, and for all, so in fact, all the safety critical system, they are protected through diversity and redundancy, and they are the fundamental design principles. Other than the quality and single failure criteria. Single failure criteria means one channel, one component failure should not lead to the undesired consequences. So more than one, two, or sequence, and that includes human error also. So human factor. So if everything fails, then human takes some action and bring the plant to normal state. So if that fails, then it's problem. And but then one thing also you must understand: during emergency, the stress levels are generally very high. So it affects the human performance capability also. So system should be designed in a manner that the systems are less complex and the operations are one or two maneuvering, and then system should take over. So here I would stop, because this was an opportunity for me to give the essence, or I would say the soul of this course. And whomsoever has taken this course, I would say they are lucky, because any field you are working in, the risk and reliability criteria you have to learn, and if you know that, you can make really good changes, in the plant, and that will result into increased productivity, at the same time safe uh, safety of the not only the occupational workers, this of the public also. And of course, we are protecting this way the environment also, because if consequences reach the public domain, then the environment, public, they also come into the picture. So the traditional definition of safety is protecting the people, property, and environment, and so many things. And then when you do this, automatically automatically your system becomes part of the sustainability. So that way, nowadays we talk about sustainability. So risk reduction, it is called de-risking. De-risking, and that de-risking means safety, improving safety, and reliability. These two, many people think they are contrary, opposite goals. No, both go hand in hand. If you improve the reliability, then the demand on the safety system will be less, and not only that, even problem in the safety system also lead to plant shutdown. So have maintained the safety system of course, safety systems are the first priority in the plant to be maintained. But then if you invest on safety, the one simple thing, or security, there is a new dimension which has come in last 15, 20, maybe around 15 years, since 9/11, it had taken the real impetus. Security is also becoming more. Now, in nutshell, I have to explain you what is the difference between safety and security. A broad difference is safety is unintended failure due to some hardware problem, or so you can call it as a random failure. Of course, there is a difference between random failure. When you are able to find out root cause, it doesn't become random. You correct it and all. But still, the random is aleatory uncertainty. Okay. And security means intended, malicious, uh, intent, rather intended failure. That means deliberately you are plugging in some failures into the system. Security aspect has to, so there is something called security audit. And then the next thing is security probabilistic risk assessment. And there are deterministic provision also. Security is all deterministic. And then we have to see effectiveness of this thing, that is through security probabilistic risk assessment. So security aspects is a new dimension, and probably we'll have a separate course on this actually, because it's very, very intimately connected topic to the system, plant, and establishments. And certain things about the system, security is a very plant specific aspect, I would say. I'll stop here. So thank you very much. I did not see any chat box, somebody. So I close here, and definitely you can ask me question by writing. But then I'm seeing some question. My only suggestion is be very specific when you ask a question. Number one, and ensure that wherever you are required to work, you have to work on it. Please understand the topic, because the intention should not be, I have not understood the first lecture. And finally, I am seeing the question which is coming. It's everything is there in the presentation itself. So whenever you are, in fact, you will not be knowing this, or maybe teaching is a learning for the instructor also. So if you ask a question, I will also learn something new. So for me, it's a benefit. But then when you ask a very specific question, I can generate a better answer. But if you ask a very general question, then I would say have the see the presentation. If it is not there, and then you can get back to me. But we'll have to remain within the scope of the our subject, that is risk-based engineering. That we must all remember. Thank you very much. Enjoy. I know it's hard work is ahead of you, and believe me, once you spend some good time on this, you'll be laced with a very powerful system with you, and we are trying to do a good job for India. So let's uh, work in the interest of our country. And risk and reliability are two important topics. India is venturing into, now next 10, 15 years, will be one of the advanced countries. So these are the tools that will make it advanced. Thank you very much.